Okay, so we're back to calculate the change in enthalpy for the combustion of methane using Hess's law instead of bond energies. Kind of the opposite of using bond energies. Hess's law has products first and then reactants. And of course you'll use table 13.2 instead of table 13.1. To find the standard enthalpies of formations of each product and each reactant. It does not, that table in your textbook does not contain the standard enthalpy of formation of methane gas, so I'm going to tell you it's negative 74.6 kilojoules per mole. You also don't have to count number of bonds when you do the math this way. So we will look at our products first. So CO2 gas and water vapor are going to be our two products. So we have, I'll put a big bracket to start with. So our two products, CO2 gas, we have 1 mole of CO2 gas times, and we look at the table, CO2 gas, oh there it is, good, negative 394 kilojoules per mole, negative 394 kilojoules per mole. Luckily our moles cancel there. And then we add up the other product, water vapor. So we have 2 moles according to the balance equation of water vapor. And water, you have to look, now there's a gas version and a liquid version. We know that combustion, of course, produces gaseous products because it is very hot when stuff burns. So we know the products of combustion will be gas, water vapor, so we're going to use water as a gas. Negative 242 kilojoules per mole. So those are both of the products, so we're done with that side. Then we subtract the reactants, which I'll have to do on the next line again. So our reactants, methane, we've got 1 mole of methane, and I told you the enthalpy of formation for that is negative 74.6 kilojoules per mole. And then we'll add the other reactant, which is oxygen. Now we've got 2 moles of that, but we know that oxygen in its elemental form O2, a homonuclear diatomic, this is exactly how oxygen wants to be. The standard enthalpy of formation is 0 for any element. This is oxygen's elemental form, so its enthalpy will be 0 kilojoules per mole. So we can cancel all of our moles and just get kilojoules. So, of course, with bond energies, you have to use the bond energy even for oxygen. But when you use Hess's law, every single thing in its own normal elemental form will have an enthalpy of formation of 0. It is the way it wants to be. It doesn't take energy to form it. So, let's see. According to Hess's law, 1 mole times negative 394 kilojoules per mole will be negative 394 kilojoules plus 2 times 242, and of course that'll be negative 484 kilojoules, and then minus, and then 1 times negative 74.6 is just going to be negative 74.6 kilojoules, and of course the 0 will just be 0 there, and that will be fine. Okay, so negative 484 plus negative 394. Oh, did it wrong. 394 plus 484. So that'll be negative 878 kilojoules minus a negative, so that'll be a plus 74.6 kilojoules. So minus a minus, double minuses make it a plus, right? Not plus or minus, but you see. Okay, so negative 878 plus 74.6. Now my calculator is going to say negative 803.4, but I don't have a tenths place here. I have significance in the ones place, so I have to round to the ones place. The 0.4 won't make it round up, so I'm just going to have negative 803 kilojoules as my change in enthalpy according to Hess's law. So, when we did it via bond energy, we got, I think, negative 802. Bond energy is negative 802 kilojoules, I think, or negative 804. It was very, very close. I don't remember if it was 802 or 804, but very, very close. So you can see that even though Hess's law is more accurate, we get pretty close either way we do it. Also, make sure that you understand the significance of what it means that the delta H is negative. When enthalpy is negative, that means that heat is what? Lost or given off to the surroundings or taken in. When delta H is negative, that always shows that you have an exothermic reaction. Okay, because all this heat is given off to the surroundings. It's combustion. We aren't surprised that it's exothermic, right? But when delta H is negative, heat is lost to the surroundings. It's exothermic. That's a good way, if you can think through the reaction and say, I know combustions are going to be exothermic. If you have a delta H that's negative, that's a good check to make sure that you're on the right track. If I had gotten a positive number for delta H for a combustion reaction, I would be very doubtful about my work, and I would check through to make sure I didn't make a mistake somewhere, like a double negative mistake or something. So clearly this should be exothermic. It is. It's very close to the other number we calculated for bond energy, so we can have pretty good confidence in our work. So I will probably stop this video now and come back with some practice problems in a bit.